So our main event, we're happy to have Kurt Simon again speaking. You know, he's been a longstanding club member, and he has, I'll repeat this, he spoke on the first part of this talk. Weird Science Part 1 was in January. And today he presents Weird Science Part 2, focusing on the micro instead of the macro this time. And we'll talk about the wave theory of matter. And if you didn't think that an electron could be made up of waves, he'll tell you all about that. What? We'll just wait. More than just electrons too. So Kurt has a PhD in systems engineering from UCLA. He worked for Rocketdyne on the rocket engines that went to the moon. He worked for 31 years at TRW developing data systems and satellite-based image and signal collection systems. But wait, there's more, right? He might tell you about that. So our club is blessed with having so many people with backgrounds like this, and not just science backgrounds, but it's a fun place to be. So anyway, let's welcome Kurt.
I said this before, but I'm an engineer, not a scientist. I expect reality to be logical and not mystical, describable by mathematics and intuitive. Modern physics is not. It forms a perspective on reality on the largest and smallest scales, so to speak, unknowns and weird concepts. I gave a presentation earlier on weird science at the cosmological scale. You can actually find that on the Nevada County YouTube channel, if you didn't know we had one. This is my promised presentation on weird science at the smallest scale, particle physics. It's a pragmatic perspective on reality that my physics PhD friends won't even discuss with me. It doesn't involve billion-dollar particle accelerators. But to me, it makes sense and drives all we know about particle physics from simple concepts. So hear me out. Okay, for you astronomy on tap devotees, this made a lot of sense to me. I've been working to unify relativity and quantum mechanics into a single theory of everything. So far, I've discovered beer is good. So if you enjoy astronomy, you'll enjoy Astronomy on Tap, the local brewery. We do that on the third Wednesday of every month.
2 weeks from
2 weeks from now. Okay, so here's my claim. The standard model of physics at the particle level is weird. The standard model includes 17 fundamental particles. That means particles that are not made up of something smaller. And they're all required to build our reality. And if you count colors and flavors on those particles, there's actually 57. There are 4 fundamental forces, not interrelated: electromagnetic, strong, weak, and gravity. I'll talk more about that. We know about the dual slit experiment, where if you fire photons or electrons at 2 slits, behind the slits on the screen, you'll see wave properties. So are those photons or electrons particles, or are they waves? If you try to describe particles by the standard model, by mathematics, the only approach they have at this point is string theory. That requires that you believe there's an extra 6 dimensions out there that we can't see. There are numerous fundamental constants, all of which describe the universe, all of which are measured, not derived, and they're all critical values for our existence. If you change the charge of an electron by 0.1%, well, we won't be here. And then for quantum theory, you've got all the quantum uncertainties, probabilistics, weird action at a distance. And Einstein died not having been able to tie together general relativity and quantum theory because it's still considered incompatible. Quantum theory itself is weird. I don't know if you know Timothy Ferris, but he's an outstanding amateur astronomer who has written several books which are outstanding. One of them was called Science of Liberty, how our concepts of liberty are all formed by our concepts of science. Also, Seeing in the Dark, Coming of Age in the Milky Way, and 9 other books. And he said, quantum weirdness implies that the logical foundations of classical science are violated in the quantum realm. And quantum weirdness is so counterintuitive that to comprehend it is to become confused. Niels Bohr, one of the early investigators of the atom in its form, said, if someone says that he can think about quantum physics without becoming dizzy, that shows only he has not understood anything whatever about it. Richard Feynman, who's one of the more brilliant American physicists involved in the Manhattan Project, said the theory of quantum electrodynamics describes nature as absurd from the point of view of common sense, and it agrees fully with experiments, so accept it as absurd. Quantum systems are non-local, probabilistic until measured. That means that, and there's several interpretations. The Copenhagen interpretation explains that a quantum particle does not exist in one state or another, but in all of its possible states at the same time. And the only way you find out what state that it really is in is through observation. Observation is needed to collapse the wave function and see the reality of the state. The many worlds version says, well, there's many parallel worlds out there, and so all of the possible states of the quantum particle are in one of those parallel worlds, none of which makes much sense to me. Albert Einstein died saying, God doesn't play dice. In other words, the world is not probabilistic, it's deterministic. And spooky action at distance, being able to transfer information at greater than the speed of light by quantum phenomena. So I said, well, perhaps there's an alternative perspective on reality. You know, reality is what it is, but we then try to come up with theorems and equations and a whole bunch of things to describe what that reality is and how it will project into the future. And you can have multiple perspectives. The ones that do the best job of projecting into the future are the ones that we keep. Well, consider the following alternative perspective to the standard model and quantum theory. There's only one fundamental particle, the neutrino, actually, from which all other particles are assembled, including electrons, protons, neutrons, quarks. All matter is standing longitudinal waves in ether, and I'm going to talk more about this, all this stuff. Photons are transverse wave packets in the ether, which does exist. We'll talk about that. There's only one principal cause of motion or force, and that's minimizing wave amplitude in these in this wave space. And all physical particle and force constants can be derived from 4 wave constants, namely speed of light, the fine structure constant, Planck's constant, and the electron radius, or equivalently longitudinal wavelength and amplitude, ether density, and the speed of light c. So why do we have that? If this were true, if you could come up with this, which agrees with measurements and projections and all that sort of thing, why do we have this complicated standard model? And once you have a collider, every problem starts to look like a particle. If you're spending billions of dollars smashing particles together to find out how the world really works, you don't want to listen to people who say, wait a minute, it's a lot more simple than that. Again, I'm not a physicist. So here's the outline of my presentation. Number one, I'm going to talk about the ether really does exist. If you remember Michelson-Morley when you were in high school, or some of you in kindergarten, when I was in high school, Michelson-Morley proved there wasn't an ether, except they did it wrong. And I'll talk some more about that. Then I'm going to talk about particles being standing longitudinal energy waves which permeate all of space. Traveling waves cause forces, electric, magnetic, strong, and gravity. The weak force isn't in there because it's not one. Neutrinos, which are the fundamental particle, combine to form electrons. Electrons combine to form protons and neutrons. And I'll show you that electrons are actually probably quarks, or quarks are probably electrons. And spin of the particles, and I'll show you how that happens, actually causes transverse energy waves, which includes the strong force, photons, magnetism, and I'll show you all those forces, and in fact contributes to gravity, which is a force, not a warp, it's a force in the wave theory. I've actually spent several months trying to distill a several semester course in physics and copious mathematics into an accessible perspective on wave theory of matter. So I've avoided equations as much as possible and have skipped many interesting features and conclusions of the theory in order to shorten the presentation. But here's a top level description of what I think is a coherent perspective on particle physics. In fact, I often hear of new physics results where they come up with something to explain something or other, and I listen to it and I say, it's a lot easier to explain that by waves and wave theory. So this is not recent theory. Louis de Broglie actually showed that all matter is composed of waves and gave the wavelength in terms of their momentum. This in practice only works for very small particles. Erwin Schrödinger wrote an equation which describes the form of the probability waves or wave functions that govern this motion of small particles like electrons. It specifies how these waves are altered by external influences. Huygens proposed that light is a longitudinal wave in the ether medium. The set of particles oscillating in phase with each other is called a wavefront. Point sources in that medium give out spherical wavefronts. Gabriel LaFreniere, I think he was French, but I can't swear to that. His original website was written in Russian. Well, he died in 2012. And fortunately, a bunch of other scientists grabbed a hold of the website, converted it into English. Jeff Yee picked up on that with several other people, wrote a couple of books, Particles of the Universe 1 and Particles of the Universe 2. 2 is a more coherent version. He also has a website and YouTube videos and all kinds of information where you can get more. I'll show you what that is later. So let me start with the discussion of the ether. So Michelson and Morley, the way they decided they were going to show whether there was an ether or not was they built a device that had two shafts, one going out this way and one orthogonal going out that way. And they had a beam splitter at the joint, and they had reflectors at the ends of the tubes. And so they would shoot high frequency light beams into this thing, which would go down both tubes, bounce, and come back. And since the length of those tubes was the same, you would expect the light pulses to come back at exactly the same time and in phase, unless one of those was moving in a direction in the ether, in which case you'd expect some Doppler effects, which would change the timing, and they wouldn't come back at the same time. Well, it turns out no matter what direction they pointed this thing, they didn't get any shift. And many, many people repeated this test. Unfortunately, the test could not show whether there was an ether or not Ethernet, because Dirac, what was his first name? Hendrik Lorentz. I'm sorry, Hendrik Lorentz wrote an equation which was the basis of Einstein's general theory, special theory of relativity, which said that as you get up to close to the speed of light, time will slow down for you relative to a stationary observer, and lengths will foreshorten. And that's a whole presentation briefing on itself. But he pointed out that if this device was moving through the ether, then the relativistic foreshortening would change the length of the shaft so that you would not see any time shift in the returning light pulses. So the device was incapable of showing motion through the ether. There is science before Michelson-Morley, and there's science after Michelson-Morley. After Michelson-Morley, most of science said, well, there's no ether out there, nothing must be waves, everything must be particles. And so they went into quantum theory to define all those particles. But it turns out that there really is an ether. Let me talk about that.
Question. So you were saying that I think Michelson-Morley was talking about, because the Earth is traveling through space, that there should be
through the ether.
And it can, so you're saying that it is active, the length contraction, whatever that alters the waves, exactly cancels out the wave shift?
That's what Lorenz said.
And it turns out to be not the case.
Yeah.
Right. Plus the Earth spinning, right?
Right.
So you could not detect the motion because of the relativistic foreshortening. So the test was faulty. It didn't prove there was or wasn't an ether. But on the other hand, if we have all these electromagnetic rays and solar rays and all this other, all of which are waves, electromagnetic waves, what's waving? You know, they just recently discovered the Higgs particle. Well, they actually discovered evidence of the Higgs particle, which is supposed to give everything mass. And the Higgs field permeates everything and somehow or other, I don't know how, gives mass to particles. Well, what's the difference between that field and an ether? So we're postulating an ether here that consists of granules all packed together, much like water molecules in water. And you can jiggle a particle, they call them granules, jiggle a granule over here and it passes that on all the way through. And so you get energy transfers through this ether, much the same way you would get by dropping a golf ball in the pond over here and getting a ripple over here. In addition to that, in this ether, postulated ether, there are wave centers. These are places in the ether where waves come in and bounce off. They don't just transfer on to the next granule. So you have all of these granules stacked together and you have wave centers that reflect them back. So energy flow examples. Example one, you got two granules, one hits the other one, bounces off, passes that energy on, goes down through the ether as an energy wave. Where do these waves come from? Big Bang, who knows? The example two, you've got a wave center, it doesn't bounce. It bounces off and goes back. So you end up with an incoming wave and an outgoing wave. And the combination of those looks like a standing wave. And I'm going to talk about standing waves. Let me talk about wave dynamics first. There are two kinds of waves. This is where the hand waving comes in. You have longitudinal waves, like sound, where the waves are going in this direction and the particles are oscillating in the direction of the wave. Sound does that. There's also transverse waves, like you shake a rope, where the particles are going this way, but the wave is going that way, orthogonal. You can also have traveling waves where the waves continue on down, or you can have standing waves. And I'll give you examples of both of those. The longitudinal standing waves at wave centers store energy and thus mass. Mass and energy are equivalent. Eventually they transition to traveling waves. Electromagnetic waves have both longitudinal and transverse waves. And interacting waves cause forces by trying to force particles onto minimum amplitude places, nodes of these waves. I can't see my, oh, there we go. Okay, here's traveling waves. If you look at, I don't know if you can see them. Let me see if I can see them. Look at the red particle. Particles just going back and forth like this. All of these particles are just going back and forth like that. But they're all in sync. And so you end up with a peak density that's going off this direction. So there's your wave velocity. And the particles are in the same direction as the wave velocity. So now let's take a look at transverse waves. So here are transverse waves. The particles are going up and down. But if you look at the peak of the wave, it's going this way, and the particles are going that way. So those are transverse waves. This is important because transverse waves turned out to be photons and other things. And the longitudinal waves contribute to matter. Let me give you another example of standing waves. So here, if you look at the blue sine wave going over that direction, it hits this wall and reflects into the green. You see it reflecting off into the green. The green's going off this way. If you add those two waves, they give you the red wave. You notice that the peaks and troughs stay right where they are. Those waves are not moving, they're standing. So here, same particles going back and forth, and the waves are not moving, they're standing. So we have energy wave laws. I'm not sure how you prove these, but they seem logical. And with these laws, you can derive all of modern physics. Energy waves travel throughout the ether at a defined wave speed, namely c, and wavelength, and we'll talk about that, as wavelets to form a wavefront. Ether granules are the medium that respond to wave motion such that it can pass its inertia and momentum to the next granule, thereby getting energy transfer. Ether wave centers reflect waves and may assemble in formation multiple centers to create particles via constructive and destructive wave interference. Ether wave centers move to minimize the amplitude on the wave, preferring the node position of a standing wave, thereby creating forces to move the particles around. And the wave energy is proportional to its amplitude, wavelength, wave speed, and density within a given volume. So here are the four fundamental wave constants. Now, remember I told you there's 57, I forget how many fundamental constants we have in the standard model. Here we have four. We've got wavelength, turns out to be exactly the same as the electron radius, with some conversion of units and what have you. The amplitude is the well-measured fine structure constant. What in the world is that, you say? If you didn't say that, I just did. That's the fine structure constant is worth a briefing all on its own. If you've read Hitchhiker's Guide to the Galaxy, Douglas Adams, you know, they're going out looking for the answer to the ultimate question of the universe. And finally, towards the end of the book, they discover it's 42. That was wrong. It should be 137. Look up 137 on the internet. You'll find it's the fine structure constant. It's actually the strength of the coupling of an elementary charge E with the electromagnetic field, or it quantified the gap in the fine structure of the spectral lines of the hydrogen atom, and that's why it got the term fine structure constant. And its dimensionless value is 1/137. It's the wave amplitude ratio between the electric force, which is spherical and longitudinal waves, and the strong force, which are axial transverse waves. the geometry change from spherical to transverse waves, if you work it out in trigonometry, can be expressed as 4 pi cubed plus pi squared plus pi. And if you calculate that out, it's 137. Okay?
You talk about the electron radius, and I don't pretend to understand how this could be, but I've been told that the electron is zero-dimensional.
No, it does have a definite radius. Repeat the question. You're told that the electron has a zero radius.
That is zero-dimensional.
Zero dimensional?
Yeah. I don't pretend to understand that.
Yeah, I don't think that's correct. But let me go a little bit further, because I'm going to show you a model of the electron formed from neutrinos. And I think you'll see that it does have dimensions. And in fact, the radius of the electron is well known, well measured. It's not the number here, 2.8 times 10 to the minus 17, because there's some multiplication of some other parameters in there. Notably, K is the number of fundamental particles in an electron, and K is 10. So I don't want to get too much into equations, but let me show you the model of the electron, and you'll see that it indeed does have dimensions. Density is the well-measured Planck constant. Where did that come from? Well, the only place I know it came from originally was it's the constant that relates the energy of a photon to its frequency. E equals h times frequency. And then the velocity is the speed of light. So you have these 4 fundamental wave constants from which you can derive all those other constants, and all of the papers and websites that Jeff Yee has out there show you all the equations for doing that. And I'm not going to get into that. I'm not going to do that. Take my word for it. So the fundamental particle is a standing wave, the reflection of longitudinal energy wave at a wave center. The calculated energy, when you calculate that energy, comes out to be 2.39 electron volts. And that's very close to the measured energy of a neutrino. Neutrinos happen to be fairly small. 10 to the 26 of them will make 1 grain of sand. Photons, on the other hand, are packets of transverse energy waves, and they're caused by a particle's vibration or spin, and I'll show you that. This sort of resolves the dual slit quandary of our photons, particles, or waves. Yes, they are. They're the same thing. Particles are waves. So particle creation. You can combine a number of wave centers together in a particle. So if you have 2 wave centers, the mass of that combined particle goes up, the amplitude increases, and the particle radius increases by the number of wave centers. So if you have 2 complex particles with multiple wave centers close to each other, their combined longitudinal waves will combine at an increased amplitude, and that increased amplitude between them will force the particles away from each other. So like charges repel. If one of the particles is an antiparticle, like a positron, which means it's formed on the node of the wave, which is 180 degrees away, so it looks like the reverse, then you get decreased amplitude in between them, and they'll be pulled together. So particles consist of a combination of wave centers, which is called K here. The energy of the particles can be calculated based on standing wave energy, the longitudinal energy equation. So you see on the picture there, you have standing waves around the wave centers. Let me say there's 10 of them in this case. And as you get away from that, they decay into traveling waves. There are precise equations for the longitudinal energy equation and the transverse energy equation. I'm not going to go into these in a lot of detail, except to point out that the only thing that's in these equations that isn't in those four constants I talked about earlier is K, which is the number of particles. So if you have 10 particles in 10 wave centers in your particle, K is 10. The summation of ends there brings in different shells of the electron, the contributions, and I'll show you that in a minute anyway. At any rate, the equations are fairly simple, but there are similar equations for the electric force, magnetic force, gravitational force, strong and orbital forces, and photon frequency and wavelength. And he's worked all of these out, and they all come out exactly right. The mass of the combination of wave centers grows as the fifth power of the number of wave centers. So if you have 10 wave centers in your particle, its mass is going to be 10 to the fifth greater than one of the particles. So this is how a bunch of very light neutrinos can combine and form a much more massive electron. And I'll show you also how electrons can combine and form much more massive protons and neutrons. So let's talk about electrons. Electrons, the wave center count is 10. And the way you get 10 of these things on nodes of the longitudinal waves going through it so that they're stable is you put them in a tetrahedron. The bottom layer of the tetrahedron has 6 wave centers in a triangle, 1, 2, 3. The next layer up has 3, and the next layer up has 1. That's a total of 10. So it's a tetrahedron of equally spaced marbles, you can look at them like, but wave centers. In 3 dimensions, then, most of the wave centers are on wave nodes, as you can see on the waves going back and forth. But there's an exception. Turns out that the wave centers that are on the sides, like the blue one on this screen on the bottom, are not exactly on the wave center, on the wave nodes. So they have a force to move them onto the wave node, and this causes the electron to spin. And it actually takes 2 rotations for the electron to spin back to where it was. So you can talk about half-spin electrons. So that spin then turns into other forces, and we'll talk about that in a minute. This is a simulation of an ether with an electron standing wave in the middle of it, at least in 2 dimensions. It would be hard to simulate and display in 3 dimensions, but this looks like a standing wave. So you can see after a certain number of rings here, they transition into traveling waves. So this is simulated. Here's one where they actually took a picture, electron microscope picture of an electron. It was done at London University. And if you look at it in fine detail, you can see there are 10 rings around a center, much as you would expect from 10 wave centers in the middle.
How do you get the electron to stand still?
I don't know how they did it, but it wasn't easy. And it wasn't standing completely still, but how they took a picture of an electron, I should look that up. But I did find the picture. That's not in my field of expertise. So the electron has 10 wave centers in the middle of it. So it's got all these shells, 10 of them, which go out until they transition to traveling waves at the particle's radius. This is where the radius of the electron comes in. The equation OE equals a whole bunch of stuff equals 2.13. That sums up the contributions of each one of the shells to the total energy of that, or mass of the electron. That was what I skipped over earlier. So particles combine at nodes of standing wave structures, forming composite particles to minimize the wave amplitude within the particle. So 10 fundamental particles, namely neutrinos, can form a stable pyramid of equally spaced particles forming the electron. The calculated energy, or equivalently mass, of the pyramid equals the electron mass precisely. So without going into equations, trust me that you can calculate the energy, the electron mass from those 4 fundamental constants. But not all of the neutrinos are at nodes, and as I said, it causes the spin of the electron. It takes 2 rotations to come back to the same place. So there's a conservation of energy principle here. As the waves, the longitudinal waves go through the particle, they cause the spin of the electron, which causes axial transverse energy waves going out, the red ones that go out, and sucking energy off of those longitudinal waves coming in. So you have lower longitudinal waves coming back out just from conservation of energy. Those transverse waves are the magnetic and strong forces, and the reduction in the longitudinal waves is the gravity force, and I'll say more on that. The standard model says there's actually 4 forces. There's the strong force that binds the nucleus together, the protons and neutrons, a very, very powerful force that binds those together. Then there's the electromagnetic force, which keeps the electrons in orbit around the nucleus and binds atoms together into molecules and cause sparks when you walk across a carpet. Then they've got a weak force to explain why it's easy to knock a particle out of the middle of a proton and create a neutron. You don't need the weak force, and I'll show you that in a minute. It's not a separate force. And then there's the gravitational force, which Einstein said was not a force, it was a warp. And you can look at it that way, and you can make some good predictions on the precession of Mercury by looking at it as a warp. But it also can be looked at as a force caused by wave dynamics, and I'll show you that. So here's the main forces. There's the electric force, which is longitudinal waves pushing particles to minimize wave amplitude. Gravity, it turns out, is due to a reduction in the longitudinal wave as it goes through the particle. And if you, it's a very, very extremely small force, but if you accumulate enough electrons, and protons, it becomes the dominant force, and we'll talk about that in a minute. There's the magnetic force, which is caused by transverse waves. Particle spin creates a secondary transverse outwave. That's what magnetic force is. And that's also the strong force, but the strong force is when they get particles so close together that the energy in keeping them that close together is so strong that it cements the nucleus together. It's a very high strength transverse axial force. We'll talk some more. So if there's no force, if you've got a particle that's sitting out, no other particles around it, it has no force on it. Wave centers will move to minimize amplitude, which is why they prefer the node of a standing wave. And then force is, of course, the change in energy over distance. So I put another particle off on the right there, and the wave amplitude of the combined particles is greater than the individual particles, and so it pushes the particles apart like forces repel. The electric forces, as out waves leave the electron and become traveling longitudinal waves, they constructively or destructively interfere with other waves. And you get a change in amplitude. That amplitude difference causes a force. So the electron, again, looks like a bunch of wave centers in the middle with standing waves around it converting into traveling waves. The mass of that particle then is caused by the standing waves. The charge is actually caused by the outer rings, and I'll show you. Charge is different than mass. Charge is traveling wave amplitude measured as displacement from equilibrium. So the charge is the motion of particles at the periphery of the standing waves. So here's a simulation of an elementary charge, and you may not be able to see the red particles here, but there's a particle here going back and forth, outside the, not a particle, a granule going back and forth. Charge is defined by that radius, not by the total number of wave centers in the particle, but by the displacement at the first traveling wavelength beyond the standing wave radius. So, and they calculate all the standard charges and that sort of thing, and they come out precisely correctly, again, from the equations. The magnetic force is caused by spin energy of the particle spinning again. And they calculate the energy of that magnetic force, and it comes out exactly what the standard model gives. The energy that's lost becomes gravitational. So here's your spin wave energy. The energy, there's a thing called the Bohr magneton, which measures the strength of the magnetic force. Electromagnetism includes magnetic force of electrons in motion based on velocity. So you get faster spinning if the particle is moving, and they've gone through and calculated the effects of velocity on the electromagnetic force. The amplitude reduction that you get, longitudinal waves go through the particle, they spit out the spin magnetic waves, reducing the energy coming out, results in a reduced amplitude coming out of the particle. You probably can't read it, but it says the amplitude reduction is 2.4 times 10 to the minus 43. That's not a very strong force. It's completely overwhelmed by the electromagnetic force on a particle basis. But when two particles interact, the electric force dominates. But now suppose you take 10 to the 24 particles, like maybe the Earth, and all of those electrons are accompanied by protons, completely offsetting the electromagnetic force. All you're left with is that minuscule amplitude reduction multiplied by the number of particles that are in the Earth. And you can calculate from that what the force should be at the surface of the Earth. In other words, the gravitational constant. It comes out precisely on. And they've done that for all of the planets in the solar system and come up with the gravitational constant, Newton's gravitational constant for all of the planets. So that's gravity. So you get two large bodies and they get a shading effect between them, and that really is what that shading effect is what causes them to be pulled together. So it really is a force, or it could be considered to be a force. And they got the gravitational force equation, which, as I said, works out. Magnetism and gravity are actually a result of the same energy from particle spin, but their wave types are different. Magnetism is a transverse axial wave, and it decreases with the cube of distance. Gravity, on the other hand, is the amplitude reduction of the longitudinal spherical wave, and it decreases with the square of distance. So at very short distances, magnetism is much stronger than gravity. but you get much farther away and gravity is much stronger. That's why your refrigerator magnet will stick on the refrigerator unless you take it a couple inches away and then that falls to the ground. Let's talk about protons and neutrons. So far, we've only talked about electrons. And I will declare, and you have to read the paper to see the mathematics to prove it, but 4 electrons in a tetrahedron, again, 1 here and 3 here. That's a symmetric tetrahedron, will form a neutron. And you put a proton, a positron in the center of that, and it forms a proton. That's why a proton has charge and the neutron does not. The calculated masses from the wave constants correspond to the measured proton and neutron masses. The electrons correspond to the quarks in a pentaquark model. I'll show you what the pentaquark model is here in a minute. If you don't know, whoops, let me go back one. If I can. There. Physicists believe that protons and neutrons were made out of 3 quarks, and they're all different in terms of spin direction, top, bottom, I forget. And so they've never seen a quark. You'll never see a quark come out of a accelerator collision. But they infer from the characteristics of a neutron and a proton that they must be made out of 3 components. Well, it turns out they've run some very high energy experiments which said there's not 3 quarks, there's 5. I'll get into that in a minute. So I'm going to show you that the quarks have all the properties of high energy electrons. So they may not exist at all, they may be just electrons. The spin of the 4 quarks at the vertices is the cause of the strong force.
No question. I think we learned that isn't the weight of a neutron higher than, just under regular physics, higher than the weight of a proton? And I'm looking up here and it says that, you have a tetrahedron with 4 electrons and you add a positron and it says the proton weighs more than the neutron. I'm just wondering, maybe my concept of weight is not, or mass, I'm sorry, not weight, mass.
I guess I don't know the answer to that. I didn't know that the neutron was heavier than the proton. Well, I have to do some more research on that.
Yeah, difference is the weight of an electron.
I'll have to do some more research on that.
Okay, since he asked that question, I believe the weight of an electron in classical particle physics is way less than the weight of a neutron. So how are we getting 4 electrons?
The energy required to put them so close together is so high that the equivalent mass of that energy accounts for all of the increase in mass from the electron to the neutron or proton. I'll show you in a sec. Well, okay, let me go a couple more slides here. But it's to cram these electrons so close together to make a proton takes so much energy. You have to do it at almost the speed of light to cram the electrons together that close, that the equivalent energy, when you convert it to mass over c squared, accounts for the difference in mass. And they've got the equations, they've calculated it all out, and it comes out precisely. Again, I didn't want to go, well, for one thing, I didn't want to have to learn all the equations. So let me go forward just another slide here. In some high energy particle accelerator experiments, they found 5 quarks, not 3, dubbed the pentaquark. And what happens is when you slam something into it, you get 4 quarks and 1 anti-quark. So normally they immediately go back together and the quark and the anti-quark combine together, and so you don't see any evidence of anything other than 3 quarks. but they do, they have seen the pentaquark, and it does make more sense. And if you look at the properties of these quarks and account for the mass equivalent of the energy required to put these things together, indeed you come out with these quarks are probably electrons. Let me go one more slide. The strong force that ties these together is a very strong, it's really a high force. It takes one heck of a lot of energy to temporarily split a proton or a neutron. You can bounce the quark or electron out of the middle of the proton much easier. But the strong force, which holds the tetrahedron together, if you take two particles with real high energy and push them together to a standing wave node where they're both on the same node where the amplitude is 0, you're going to get a real high peak of energy. In fact, the velocity of each electron would need to average almost the speed of light. So these were probably formed at the Big Bang. So when neutrinos were formed into electrons and electrons were bashed into each other, they formed protons and neutrons. So the strong force, what happens is you cram these together, you get this increased amplitude waveform in one dimension. It's an axial force, extremely high force. And so four particles in a tetrahedral geometry would satisfy the conditions for 3D stability on the wave nodes and would appear like a new particle. So this composite particle, the equation has three properties of the electron, leading to the possibility that quarks really could be electrons. So what we're doing is taking 4 electrons and tying them together, extremely high energy, and that energy accounts for the difference in mass between 4 electrons and 1 proton. C squared is a big multiplier. One of the things I did not put in here is that the strong force is axial. It's in a straight line. And if you look at the protons and neutrons in the core, you can pair up protons and draw a line in what direction the strong force goes in. And that tends to push electrons away from the nucleus. The electromagnetic force pulls the electrons in. The strong force pushes them out in ways that give you strange curves of plots of electron orbits around the larger atoms. But I didn't go into that here because we don't have time. So you get the strong force equation. So the weak force, the particle that's being contained inside the 4 quarks in the tetrahedron, is held in by mostly electromagnetic force. So if you get a solar neutrino come in, it can pop it out of there fairly easily. And since they've seen that in experiments, they had to account for it in the standard model of physics. So they came up with a new force called the weak force. That's the only place it shows up. And the weak force is not really a separate force in this model, but a combination of the strong and electromagnetic forces, which hold the quarks or electrons in the center of the proton shell. So boom, it pops it out. It doesn't take anywhere near as much energy to pop it out of there, but it would take a lot more energy to split these 4 quarks or electrons apart. So let me talk about photons for a minute. Particles always reflect longitudinal waves. That's the electric force. So now let's look at transverse waves. Particles vibrate. A simple way for them to vibrate is you take a particle and any particle and they smash against each other. They don't just stop instantly. They do this. And that vibrating before they stop creates photons, which go shooting out. So when you shoot a electron and a positron into each other, you'll get photons out from the reaction, and they'll disappear, but they're not gone. What's happening is their wave centers combine, and there's no standing waves there at the point. They've got the wave centers. There's no energy, so there's no mass, and they're not you can't detect them. So you consider that they've destroyed each other, and all that's come out of it is a couple of photons. Later on, another high energy photon can come in, hit those, and split them into an electron and a positron. So you have particles popping out of space from nowhere. Quantum theory says, well, that's because of the quantum uncertainty of where they are. So they depend on quantum uncertainty to describe why you can get particles popping out of space. Well, that's not true. So the particles vary up and down. They can vibrate at any speed. Another way for them to vibrate, by the way, is to change orbit around a nucleus. The electron can go up one orbit. It doesn't go instantaneously. It goes like this, and that shake is the photon that goes shooting off, or the photon that comes in, shakes it and bounces it down to another orbit level. So the wavelength is not preordained as the longitudinal wavelengths have to be some multiple of that fundamental wavelength. Photon wavelength can be anything. So photons turn out to be short-term transverse axial waves caused by particle vibration. Interestingly enough, the energy of matter simplified equation, E equals mc squared, but the energy of a photon is E equals the Planck constant times the frequency. Particle is stored energy in a sphere. The photon is vibration energy in a cylinder. And the change of geometry between those, you can work out to be that 1 over 137 fine structure constant I was talking about, 4 pi cubed plus pi squared plus pi. So the annihilation of electron and a positron creates two high energy photons. The wave centers are still there, but have no standing waves and thus no mass. And the photons come from the particle vibration until settling in place. Bring another high energy photon in, and you can create particles out of nothing, presumably out of nothing, because those two wave centers now all of a sudden have standing waves and pop apart. So we don't need the quantum weirdness to describe why particles pop into existence or disappear. Fundamental physical constants. I'm getting close to the end now. No applause. Hold your applause. Fundamental physical constants. Here's some of the constants. I know you can't read it, but I'll point out a couple of them. The electron mass, the Bohr radius, Planck time and length and mass, elementary charge, Coulomb constant, the Bohr magneton, gravitational constant. All of these things are calculated, are measured in the standard model. And the standard model says, you know, if we were off by 0.5% in any of these constants, we couldn't exist. Like take, for example, if the electron mass was slightly off of that, atoms wouldn't form. So why are they like that? Well, you can use the anthropic principle that says if they weren't like that, we wouldn't be here to observe them. Or you can take, so they have calculated all these, it's called the codata value in the middle column. Jeff Yee calculated them all using the 4 fundamental wave constants, amplitude, density, wavelength, and speed, and measured the difference. And every single one of them is 0 to several decimal points. So he was able to calculate all of these constants from the fundamental wave constants. So if you look at a comparison of the theories, the energy wave theory versus the standard model and quantum theory, string theory. Energy wave theory has either 1 or 2 particles, depending upon whether you count the neutrino as a particle or the granules and wave centers as particles, whereas string theory's got 17. Energy wave theory's got 4 dimensions, 3 spatial and 1 time. I can deal with that. If you want to go to string theory, you've got to add another 6 or 7, maybe, depending on the string theory. You can solve all of the energy wave theory equations in one set of calculations. In the standard model, you've got to go to the large scale calculations and the quantum theory calculations. There's only 5 constants theory that define all of energy wave theory. You've got more than 19 in the standard model and string theory. Standard model and string theory plays around a lot with multiverses as opposed to only the one universe we have. All the forces in the energy wave theory are unified. In the standard model and string theory, they still haven't unified all of them, in particular gravity. Particles are formed in energy wave theory by wave center combinations. And in string theory, you've got vibrating string patterns. And I think that's falling out of favor. People are starting to give up on the mathematics of that. Particle mass in the wave theory comes from standing waves. And we got this thing called the Higgs field, which maybe we have evidence of and maybe we don't. But it's, it's pretty weird. So I picked the first one. As I said, I'm an engineer. Here's some references if you want, and I guess this will be available on the YouTube channel. If you want to look at some of the mathematics that goes behind all this and the proofs that shows that the wave theory proves all of this stuff within mostly within several orders of magnitude. The original paper, Matter is Made of Waves, by Gabriel LaFreniere, was the one I said was written in Russian. When he died, several other scientists grabbed it and converted it to English, and it's out there on the web. Particles of the Universe 2 is Jeff Yee's book, and the rest of these things are done by Jeff Yee. The Introduction to Wave Theory, which is a real good introduction to what I just presented. He's got another presentation which has a different perspective on it. He's got his YouTube video, for those of you who like to watch YouTube, which describes it fairly well. And then he's got papers out there which have equation after equation after equation, deriving all of the intermediate results and proving that this is all correct. So that's all I've got, and I'm willing to answer any questions that I know the answer to, except from physicists.
Yeah, I got a softball.
All right, here it comes.
Is there anybody, are there any engineers out there in the world using this to design computers or blow things up? Whatever you might do with this theory.
Let's see. Or any application that you can think
Or
of.
any application.
Yeah.
Repeat the question.
Gary wants to know, are people using this theory for blowing things up or what have you, much as they might do with the standard model? And well, let's see, for one thing, they're not getting billion-dollar contracts to build the accelerators, but if you can drive all of the characteristics of energy and matter from a much simpler set of equations, why not? So there is a community of, I don't know whether they're engineers or scientists, who are struggling to show that indeed that this is a viable perspective on the universe that we can apply causality to, we can apply regular mathematics, not probabilistic quantum theory and string theory and all that other stuff, and derive usable results in any kind of engineering or physics, then so be it. It's an alternative perspective on the world, which is easier to grapple with. And I've heard some really strange concepts come out from somebody just discovered an effect in a physics experiment, and they come up with this grandiose explanation. And I look at it and I say, isn't that just, can't you explain that much easier with a wave?
How about quantum computing? That seems like an obvious place where it might.
I haven't seen one yet
apply.
that haven't seen one yet that's doing anything. I hope that works, but I have not seen anything that says that anybody typed out "hello world" on a quantum computer, or added 1 and 1.
What are the objections to wave theory? Why is it not acceptable to the physicists?
Well, you saw my cartoon at the beginning. Well, repeat the question. Why is this wave theory not acceptable to the physicists? And let me go back to one of my early, oh, rats, I turned it off. Oh, I just screwed up. Oh, my cartoon showed this giant multi-billion-dollar accelerator. And there's a large army of physicists and scientists who've been working on this since Michelson and Morley, trying to figure out what are the fundamental underlying characteristics of matter. And so far, all they've discovered is there's a whole bunch of different particles come out of these collisions. You can describe why all those come out of the collisions just off the wave model. Well, let's combine these fundamental particles together in different things other than a tetrahedron. But you don't keep your billion-dollar accelerator funded.
Well, you need the accelerators to at least do experiments to demonstrate the proof behind the theory.
But are they demonstrating the proof behind the theories? What they're doing is they're coming out with a whole bunch of, quote, fundamental particles, 17 of them or something like that. What did I say it was, 19? They've come up with 19 fundamental particles, and they're proving that the standard model is correct. But if you look at it right, the reason all those particles are coming out of the collisions is because we're pasting enough neutrinos together in different configurations than trapezoids that they come out looking like Higgs bosons. So are they proving the theory is correct? They're proving that their theory is correct. At least their theory agrees with what they're measuring. But what do you do with that data? If you want to project let's see, we will continue to look at the world in the context of the standard model in quantum theory. I am convinced of that, because there are enough people who want to look at it that way. But us engineers don't want to look at it that way because it's weird and it's non-intuitive, and it's very hard to predict things from it. I mean, how do you predict something from a quantum theory that says that locality is not needed, that you can instantaneously cause a flip of a spin on an electron 50 light years away by flipping one over here? You know, that's non-intuitive. It just doesn't strike my sense of common sense.
Casimir effect? Was it the Casimir effect?
Oh, the Casimir effect, yes. I thought about that all the way through the discussion on gravity. You know, you've got more pressure on the outside and less on the inside. He asked about the Casimir effect. The Casimir effect, if you take two boats and you put them close to each other, and you've got big waves on the outside, you can only have waves of a certain wavelength between them because they're only so far apart. So you have less wave energy between them than there is outside, and they get pushed together. Same thing happens on a microscopic scale. If you have energy on outside of two plates that can't form between the plates because of the distance, they'll be pushed together. It's called the Casimir effect. Well, gravity is sort of like that. You get the shading, so there's less force in between the two masses than is outside. There's a theory of gravity called push gravity, which doesn't get into the wave, where's the push coming from. But if you look up push gravity on the internet, they'll say that gravity really is having less dense whatever in between the two masses than you have outside, and that causes the masses to get pushed together.
And the other one is the black body radiation, which supposedly goes to zero. Does not go to zero.
The black body radiation does not go to zero? Okay, so what's the conclusion from that, I wonder?
I'm just bringing up subjects where there's no logical explanation.
Oh, I can't explain it, but I'm not logical. Gary.
Well, if you imagine a hydrogen atom, maybe associated with one electron or two electrons, how do you imagine the vibration occurring to the photon or the electron?
You mean if a photon comes in and pops it up one level?
Forget the photon. Is the electron vibrating with respect to the center, or is it vibrating transversely in some, or propagating in some way around the nucleus?
Well, Bohr would say it was like a planet around the sun, right?
But what would you say?
Schrödinger would say it's a complex equation, partial differential equation. Depending on how many protons you've got in the middle, you get different. You can get barbell shape for the orbits. You can get.
But we know this is a hydrogen atom, so we only have one proton.
So it would be a circular orbit. Now maybe it's, I don't know. Is it elliptical? I don't know.
Well, is it an orbit, or is it some kind of vibration, such as you've just described?
Let's see, the wave theory. So I guess the wave theory I presented there doesn't talk. There's a whole bunch of additional mathematics within Jeff's book and on his website for describing how the electrons get to where they are. And he describes them as deterministic orbits. They're not probability clouds like quantum theory would tell you, where you have to decide by observing it where the electron really is. That it really is the electrons are really going around. And what keeps them from spiraling into the nucleus by the electromagnetic charge is the strong force, axial force, pops it out every so often. And depending on how many of those strong force vectors you've got, depending on how many protons and neutrons you've got in the center, will determine what those shapes are. But he says that the electron is really in an orbit out there.
Okay.
But it would have to be not just in one plane, right? It would need to kind of move around, because the standard, the S1 and S2 or whatever, they're, I'd imagine they're spherical.
Well,
so the wave would have to be.
And again, the way they describe it is.
But it's in one place at one time.
It's a combination, yes. It's a combination of the electromagnetic force trying to pull it into the nucleus and the strong force, axial strong forces pushing them out at certain places within the orbit. And you can, depending on how many of these strong force vectors you have, which is determined by how many nucleons you have, that determines then what the shape of the orbits within
I mentioned deuterium and tritium and all that. I mean, they're probably
Yeah,
not exactly. But if they're the same, that would kind of point against wave theory, I think. So
Well,
because it'd have to be, there's extra neutrons. Well, maybe it's because there's no electrons.
Well, see, the wave theory that I've presented is talking more about what's the structure within the electron than what is the what's the interaction between the electron and the nucleons? That is all included in Yee's work, but I didn't bring it in. I had some backup slides to talk about it. I decided against it. I'll go do some more reading.
Are you
No,
saying-
you go do some more
The
reading.
next question was, if you can see the shape of the electron somehow as a wave, then what happens when a photon hits it? Photon is what you're,
It adds energy to it. It adds energy to it. When the photon hits it, it adds energy to it. And that's supposed to move it out of an orbit. You can only have discrete orbits. That's where quantum theory is correct.
and eventually another photon will pop out of it.
And then go
someplace.
back down again, yeah. But the shape of the electron is a tetrahedron with rings around it in 3 dimensions. So you got 10 shells around that tetrahedron in the middle of wave centers.
It's not a wave at all then.
No, no, it's not a wave. What it is reflections of waves that are permeating the universe. So where the waves are is permeating the ether. They started from the Big Bang. So they're not being generated by the electron. The electron is being buffeted by it. And so the wave will go through the electron and it'll be reduced in amplitude and it'll spin the electron and it'll send some axial waves out or some transverse waves out for magnetism. But the physics of where do electrons sit in a multi-nucleon atom, it depends on how much energy's in the electron, and you can pump more in by hitting it with a proton or photon, which will pop it up another quantum step. Only certain radii, because only certain radii have the right velocity synchronization. It's the Ferris wheel thing where you hit it every time it comes around. If you hit it any other time, it stops. So that.
Yeah, but by this theory, then that synchronization must be very complicated because you've got several parts of an electron and several parts of the nucleus. They're all operating within waves. So all of these converging waves have to behave properly in order to get the electron.
But those aren't causing the electron to be in specific positions relative to the nucleons. The waves are actually causing the particles, the electron and the nucleons, and their interrelationship is determined more by the physics of electromagnetic force and it can only be at certain radii for the energies to balance, that sort of thing. So that's not caused by the waves. The waves are causing the electrons and the nucleons. And then they interact because of other energy considerations. So I'm going to hand out this paper, which has 8 questions on it. Show your work. Nothing's to be left as an exercise for the professor.
Great talk.